Hi, my name is Gavin, and welcome to Design Assignment 4 for Computational Multiphysics. So this time around, we were given a piezoelectric material with an isotropic polymer deposited on either the top or the bottom. That was left to us to choose. We are applying a 1,000 volt potential difference across the piezoelectric and increasing the temperature of the scenario by 15 degrees to induce thermal expansion in both materials. We also give the geometry of both piezoelectric and the polymer. However, the polymer thickness is mutable between 20 micrometers to 2 millimeters. That is up to us to choose. And the goal of this assignment, based on the given parameters, is to find the optimal thickness that will produce the maximum transverse tip displacement in the beam. And we also given the piezoelectric coupling coefficient matrix and the compliance matrix. And in terms of what I did in this assignment, I brainstormed the initial flex. I helped them with 2D to 3D validation. In the design report, I wrote the 2D conversion section, and I did the scripting and optimization of the report. In response to thermal expansion, the polymer is going to grow larger, thus shrinking the piezoelectric longitudinally such that it contracts in on itself. This is going to cause the beam to bend downwards if we have the polymer on top, which is what we want so that gravity aids the displacement as opposed to working against the motion. So we're going to leave the polymer on top due to that. If we take a look now at our strains caused by the electric field thanks to the D matrix, we can see in the X direction we find the largest strain effect due to a Z-oriented field. So we're going to orient our electric field in the Z direction. Then using concepts from statics, we incorporate this model into Maple and come up with a test values to compare. In simulating, we initialize our variables and geometry. Then we draw our shapes and define our extrusions. Here's the shape now seen, the limited regions corresponding to each material's parameters. Here we define the displacements, and then we find our stress-strain coupling alongside the piezoelectric stiffness matrix, which is derived in Maple. Then moving down, we have our strain definitions, mechanical strain definitions. Here is a visualization of the thermal expansion effect. We can see the piezoelectric contracting on the bottom. If we move down here, we're defining now our D matrix and mechanical strain to simulate the electric field, which then amplifies this tip displacement. And the discrepancy we account for is due to the Z axial strain from the applied field, this term right here. And if we remove that and simulate it, we get very consistent results with our Maple and Flex. This graph here shows the independence of the tip displacement alongside Y, where this is a very small difference, and it's plotting this line over here. So we can thus declare that it's okay to simulate it in 2D. To do that, we have to remove every column and row that these highlighted Y-dependent axes fall on, and then every instance in which those variables appear, and that just generates a simulation like this. To validate these models, we're going to plot the transverse displacement alongside all of X for various thicknesses. So at 20 micrometers, here we see these two plots for 2D and 3D respectively, very similar values. Now for 200 micrometers, 2D and 3D respectively, very consistent values. Now for 800 micrometers, 2D and 3D respectively, very consistent values. For 1.4 millimeters, 2D, 3D, very consistent values. And for 2 millimeters, 2D, 3D, and very consistent values. So they are now validated, and here are them plotted together. We can see very small difference between them. So for further validation, we're going to compare just the strain with gravity. In theory, our flex matches what we find. Then if we increase the gravity, you expect to see a big increase in this value, which again, we do see in that scaling case. Now we're going to compare just the effect of the electric field. When we do that, we see consistent results there, and we perform the same thing with multiple thicknesses, all consistent. Lastly, we're going to observe just the temperature change effects, and again, we see consistent values across flex and theory. So for scripting, we initialize our library as an empty list. Here's the flex code as a string, and then we refine value function, which extracts a general value that we want from the output flex file. Our get simulation values will return us the values from our current simulation. So this takes the polymer thickness and gives us the displacement. That does in flex. The grid search function here just executes a grid search based on the step size and the bounds that are inputted with it. The zoom function takes that grid search, iterates it, and zeroes in so we can find a maximum. Scale data just scales the data list for the graph function and makes use of it down here. So then we can graph anything. Graph is pretty general. And then the curve fit function here, it takes 5 points around our maximum, and it fits a curve of 50 points to whatever value that was. And then we get our trend there. The clear function just clears the data. We have end message just produces an end message, and main is our overall function to execute the program, which when we do, we get these graphs. Transverse tip displacement, and this is the curve fit graph. So if we orient the field in the negative Z direction to strain the beam in the same direction that we are bending due to the thermal expansion and the gravity, this will be our maximum curvature condition, and thus when we execute the simulation, we find a maximum transverse displacement of the tip of the beam of negative 682.4872 nanometers in the Z direction when the polymer has a thickness of 580 plus or minus 20 micrometers, where the uncertainty arises from the step size difference.